Chapter 8, Section 5 deals with the topic of inelastic collisions in one dimension. An inelastic collision is a collision that does not conserve kinetic energy. So we talked in the previous section about elastic collisions in which kinetic energy is conserved. That's the definition of an elastic collision. An inelastic collision is a collision in which kinetic energy is not conserved. So here's our picture again. We have mass 1 traveling initially with a speed v1 and mass 2 traveling initially with a speed v2. Mass 1 is going to collide with mass 2, and after the collision they each have a new velocity. Mass 1 has v1 prime, mass 2 has v2 prime. Now we still have momentum conservation. So the initial momentum, which is mass 1 times his velocity plus mass 2 times his velocity, will equal the total momentum after the collision, m1 v1 prime plus m2 v2 prime. Now one side note here, in the previous video I drew v1 in the opposite direction, I drew v1 prime in the opposite direction, which does happen in a lot of collisions. But I want to point this out so that there's no confusion. Remember that this is a vector equation. Momentum is a vector, and so this is a vector equation, which means direction is important. So while it's still true that momentum is conserved, so the initial momentum before the collision equals the final momentum after the collision, if v1 prime is pointing to the left after the collision, then v1 prime will have to be a negative number. That's in the previous video and in the previous document. All right, so let's get back to this topic. So we have momentum conservation. Initial momentum of the system before the collision equals the final momentum of the system after the collision. Because it is an inelastic collision, kinetic energy is not conserved, which means the kinetic energy before the collision does not equal the kinetic energy after the collision. So what that means is we do not have this extra equation to help us solve problems. We only have, in general, one equation with two unknowns. We normally don't know either velocity after the collision. So we have to be told something else about the problem. We may be told what one of the velocities is and asked to find the other velocity. But a common occurrence in this type of problem is that the two objects will stick together, and when they do stick together, that's a special case of inelastic collision called perfectly inelastic. So before the collision, mass 1 has a velocity v1, mass 2 has a velocity v2. They collide and they stick together and move off with a common velocity v prime, meaning both of them are moving at the speed v prime. So then our momentum conservation looks like this. The momentum before the collision is mass 1 times his speed plus mass 2 times his speed. After the collision, they're stuck together, and so the system has a total mass m1 plus m2 moving at this one speed. Chapter 8, Section 6 deals with collisions of point masses in two dimensions. In a collision, we have momentum conservation. Initial momentum of the system equals the final momentum of the system, or momentum before the collision equals momentum after the collision. This comes from the fact that during a collision, there are no external forces, no net forces on the system, and that comes from Newton's third law. If I define the system as the combination of masses, whatever mass 1 exerts on mass 2 will exert exactly an equal and opposite force on mass 1. And so the sum of the forces, or the net force on the system, is 0, which means the change in momentum is 0, which gives us momentum conservation. Again, momentum before the collision equals momentum after the collision. Now, these are all vector equations. Up to this point, we've dealt with them in one dimension. Because they're vector equations, they also apply in 2 dimensions and in 3 dimensions. So we can have a collision where mass 1 is traveling at a velocity v1 in a certain direction, collides with mass 2, and after the collision, instead of the masses moving in the same straight line, mass 1 may move off in one direction while mass 2 moves off in a different direction. This is an example of a 2-dimensional collision. Now, in the 2-dimensional collision, we still have the possibility of an elastic collision or an inelastic collision. In an elastic collision, the kinetic energy before the collision equals the kinetic energy after the collision. In an inelastic collision, the kinetic energy before the collision is different from the kinetic energy after the collision. Now, there is a special case where if the collision is elastic and mass 2 is at rest and the masses are equal, then there's a relationship between the two angles, theta 1 and theta 2, in that they will make a right angle. In this picture up here, if these two masses are equal and it is an elastic collision, mass 2 is initially not moving, then this will be a right angle. Theta 1, the direction in which mass 1 is moving after the collision, and theta 2, the direction in which mass 2 is moving after the collision, will be 90 degrees apart.